Hello, so today's topic is the binomial theorem. So first we're just going to look at Pascal's triangle, okay? So Pascal's triangle is a pattern that kind of follows the shape of a triangle, hence Pascal's triangle, and the numbers go as follows. And the first row is just 1. Second row is 1, 1. Third row is 1, 2, 1. And the fourth row is 1, 3, 3, 1. So if you haven't spotted what the pattern is yet, well, the pattern is the two numbers above will add to the one number below. So for example, here 1 plus 1 gives you 2, 1 plus 2 gives you 3. So the next row will be 1, 4, 6, 4, 1, and 1, 5, 10, 10, 5, 1. So that's the Pascal's triangle. So next to the right, we look at our binomial expansion. So when we have x plus y to the power of 0, well, anything to the power of 0 is just 1. And when it's to the 1, sure, that's fine. Once we have something to the degree 2, we can still use FOIL to easily multiply that out. But once we get to 3, 4, and 5, before we used to have to, x plus y, so for example, for degree 3, we would get to x squared plus 2xy plus y, and then, we'll multiply x plus y. To have degree 4, we'll multiply x plus y again, and it's a long, lengthy process to expand and simplify. But if you look at it here, there's actually another pattern that emerges. When we looked at these highlighted parts, which are the coefficients, you'll see that, hey, they are basically the numbers from Pascal's triangle. And there should be another pattern that you should see, or another trend, which is when you look at the x exponents, can't spell, exponents, you'll see that for each of the degrees, as you go from left to right, the numbers are going down. So 3, 2, 1, 0, 4, 3, 2, 1, 0, etc. So as you're going from left to right, it decreases. And then when you look at the y exponents, well, as you go from left to right, 0, 1, 2. 0, 1, 2, 3. Well, in this case, it increases. So knowing this particular pattern, and it increases not randomly too, right? It increases by 1 and it decreases by 1. So knowing that the coefficients are from the Pascal's triangle and our x and y exponents have that pattern, we can figure out basically the expansion for all sorts of exponents. So right now we're just going to look at the next one here, when it's x plus y to the 6. So we're just going to go one at a time. So for our first one, we have, is just going to be 1, right? And our x is going to be the same number as our degree, because with degree 5, it was just 5. So in this time, since it's degree 6, it'll be x6. Now, degree 6 is basically just the next row, right? So therefore, we know the next one must be 1 plus 5, which is, 1 plus 5, which is 6. That's our coefficient. And x is going to go down by 1, y is going to go up by 1. You don't actually have to write the 1, but I'm just going to write it down anyway, just to show you for now. The next number will be 5 plus 10, that's the coefficient, so it's 15. X down another 1, y up. Next one, we have 10 plus 10, that's 20. X goes down another 1, y goes up. And then the next one is back to 15. X goes down another 1, y up. And then next is 6, x down 1, y up 1. And last but not least, we're at 1, y 6. So that's an expanded form. And instead of having to multiply each bracket out, there it is. So now we're just going to take it one more step further. Well, we know we're not always going to have x and y in our binomial. There's many other combinations. So here we have 2x minus 3y. But we can simply just use some substitution and look at this one. So if we think of the 2x minus 3y as x plus y, what would each term mean? So this is basically equivalent to our x, and here we could think of this as our y. So our y is just negative 3y. So knowing x is 2x and y is negative 3y, we could just replace it into our equation from above. So I basically have 2x to the 6. Oh, I'm actually going to give myself some room. So 2x to the 6 plus 6 2x5. Oops, not y. It's negative 3y plus 15 2x4. Oops. Negative 3y 2 plus 20. Unable to write here. 2x to the 3, negative 3y 3 plus 15 2x2, negative 3y 4. Running out of space, going to go into the next row. Plus 6 2x, negative 3y 5 plus negative 3y 6. And if you multiply it out, because we do need to simplify this, you're going to have 64x to the 6 minus 576 x5y plus 216 x4y2 minus 4320 x3y2 plus 4860 x2y4 minus 2196 xy5 plus 729y6. Okay? So that is still, even though it's still a lengthy process, it's much faster than multiplying each binomial out. So that leads us to, let's look at the Pascal's triangle in another way. So remember from the last section, we looked at combinations, and that's what these brackets mean, right? So basically this guy here is just 1C1, okay? That's just another way of writing it out. So we're just going to look at each of these. So remember the first row is basically the coefficients for x plus y to the 0. The next one is x plus y to the 1, x plus y to the 2, etc. And these and the coefficients can also be figured out through using combinations. So when we look at it, when we have degree 1, it will always match up with that number above. It's always the degree. And down here, it's basically going to be the coefficient, the number related to the term within our equation. So I say this is basically the term, whichever term in the expanded form, and then minus 1. So for example, the one I'm looking at here, it's even though it's going to be the coefficient of the second term, we look at 1. So it's 2 minus 1 gives you 1. Or you could think of it as the exponent of y. Okay, so for example, it's probably a bit more clear if I go with the x plus 2 example. So x plus y to the power of 2, this is basically x squared plus 2xy plus y squared, right? So if we're looking at this second term here, to get the coefficient of 2, this is our degree, right? This is our degree. And then this one, even though we're looking at the second term, it's 1. And we see that it is also the same as the exponent of y. So when it comes to looking at Pascal's triangle, there are 2 different patterns. We've already talked about it. I'm just putting it into more of an equation form, okay? So as you can see, it does have a symmetric pattern. So I'm just going to go back up to the first one. As you can see, if we kind of drew a line down the middle, if we can think of it as a line down the middle, right? You'll see that what's on the left side is the same as what's on the right side, right? There's a 5 here, there's a 5 here. There's a 10 here, there's a 10 here. So it's symmetrical once you go to the 2 sides. And basically, the example I'm going to use are just these 2 right here. So basically, 5c2 is equal to 5c3, right? That's an example. This is our 10, and we know they both equal to 10 from before. So if we put this into kind of a general equation, we could say NCR is equal to NCN minus R. Because, well, 5 minus 2 gives us 3. Another pattern that we have is the one for how we figure out what number comes in the next row is the recursive pattern. So we know that the 2 numbers above, actually I'll write it this way, the 2 numbers above will add to the number below and form a kind of triangle that way. So in our example here, we're going to say, well, 5c2 is the sum of 4c1 and 4c2. So again, when we put this into a general equation, it's basically NCR equals to n minus 1. It's always going to be 1 row above, C 1 number below it, plus NC n minus 1, so 1 row above, and the same term. And those are the 2 different patterns we have for the Pascal's triangle. So in general, we have this kind of big general equation, which looks really daunting, but we've actually talked about all of these things already. It's just writing it in a general form. So we know when we have some degree, the number that we choose, remember, this thing is basically just n0, right? That's what that's trying to say there. The number on the top, or the terms we're choosing from, is going to be the same as the degree. And for the first term, it's always going to be the number minus 1. So the first term is going to be 0 for the number that we choose from. And then when we look at our x, well, it's always going to be the same as the degree to start. And our y is going to start at 0. But as we go to the next term, the number we choose from will go up by 1 plus 1. Our x is going to go down by 1, and our y will go up by 1. Okay, so those are the things that we've already talked about, but it's just writing it all in a general form. No, you do not have to memorize this. This is just another way of kind of summarizing what we've talked about so far. So, some important points. Oh, let's zoom out a little bit. Some important points. So, when you expand it, you should notice that, actually, no, let's actually go back up. So, when we expand it, when we have degree 0, we have 1 term. Degree 1, we have 2 terms. Degree 2, we have 3 terms. And as you can see, just going back here, expansion contains n plus 1 terms. The number of terms will always be 1 more than the degree. Next, the number of objects k selected in combination nck can be taken to match the numbers of factors of the second variable selected. Basically, what they're trying to say here is if you think of the combination as nck, so that second, oh yeah, just erase this. The second point I'm trying to say, this second number here, that 1 is always going to match with the exponent of the second term, which is y in this case, right? So if it's 2, this is our k, here. Next, the sum of the exponents in any term of the expansion is n. So what we're trying to say here is, well, I don't know, does this show? Oh yeah, it does. So when we add the two exponents, so let's just use, the second one as an example again. The exponents of x plus the exponents of y, it will give you n, right? Because n minus 2 plus 2 is n. And finally, this part you do need to know, you want to write this down, is the general term for finding just one specific term is when we have some term k plus 1, it's equal to n c k x n minus k y k. So the k, the term, is always going to be one number bigger than the k because we've already established that that number, this yellow number we've highlighted there, is always going to be one lower. So the example I'll have is, let's just say example 7th term in x plus y to the 10, for example, right? So we know we're looking at T7. That's our 7th term. The number that we're choosing is degree 10, and k is going to be one lower than the term we're looking for. So we're looking for the 7th term, so k is actually 6. So it'll be x 10 minus 6, y 6. So basically, that is basically 10c6, x4, y6. Okay? Oh, and I guess we should figure out what 10c6 is. I'm just going to take a calculator and punch that in. 10c6. So I'm actually going to change that out. So basically, that's 210. All right, so let's look at this example here. For the expression a minus 2 over a to the 6, how many terms are in the expansion? Well, degree 6. So it's going to be degree plus 1, which is 7 terms. So now we're just going to use the binomial theorem to determine the first 3 terms. So again, it's still looking at that same binomial from there, okay? So for the first 3 terms, the first one is going to be, the coefficient is degree 6. First term is 0. We have x to the 6. The next one is 6, 1, x2, x5, y1, plus 6 to the 2, x4, y2, right? And now we just need to think, well, what is our x and y in this case? So our first, here's our x, and do keep the minus 2, here's our y. So that means we have 6, 0 is just 1, and we have a to the 6, plus 6, a to the 5, negative 2a, okay, plus 15, a4, negative 2a2. We can simplify. So that's what equals to this. So here, a6 is going to stay as is. When we multiply these two, this is now 4, and there's a negative sign, so it's minus 6, and multiply the 2 as well, so minus 12, a4. And the next one, we'll need to multiply this one out. So you should get 60a2, okay? All right, next one. We're going to determine the 5th term of the binomial expansion. So this is where we use that formula. tk plus 1 equals to nck x n minus k yk, right? And we're looking at the 5th term, so t5. which means we're still looking at that same degree 6 binomial from above. So it's 6. Since it's the fifth term, this is actually a 4. And our x is a. So we have a. N minus k is 2. And our y is negative 2 over a, right? Yeah, negative 2 over a. And our k is 4. So now it's just a matter of simplifying it. 6c4 is 15. And we have a squared. When we multiply this out, we basically have 16 over a to the 4. We can simplify this. 15 times 16 is 240. And a squared. Box that in. That's our fifth term. Okay, so our next question, determine the term containing a negative 4. So in this particular case, we don't know the term, so we just have some k plus 1, okay? We do know that our degree is still 6. That hasn't changed, but we don't know what k is. We also know x is still a, and the exponent will be n, which is 6 minus our k, and our y is negative 2a k. So since we're looking for a to the negative 4, or something with a to the negative 4, we'll need to put everything with base a together. So let's just kind of expand this one right here so we could separate the 2 from the a. So if we rewrite that, we'll actually get 6ck, a 6 minus k, negative 2k, and a, oops, I could just write that, a to the negative k, because we have a reciprocal. Now let's combine everything with base a together. So we have a 6 minus 2k, minus 2k. And as I mentioned, since we're looking for just the part with base a, we know that this part is just going to be some number. And this part here is also just some number. So it's really just this middle portion that will actually get to the negative 4. So therefore, with that logic, we can simplify it down to an equation saying that a 6 minus 2k must equal to a minus to the minus 4. Since we have the same base, we can just say that the exponents must equal to each other. This is from our exponents chapter. And once we move things around a bit, so we have negative 2k equals negative 4 minus 6. So that's basically negative 10, negative 2k. Divide both sides by negative 2. So you get k equals to 5. Oh, actually, no, we're not done yet. Because k equals to 5, but remember, it's tk plus 1. So t5 plus 1 is actually t6. There we go. Now we're done. So we're actually looking at term 6. Okay, last question here. One term in the expansion 3x minus b to the 8 is negative 1,701,000 x to the 5 y3. Find b. So we do know that our sum term equals to this thing. So this is sum term. Oops, that's k. This is sum term. And we have our binomial here. So let's just piece it together. So we have sum term and it's going to equal to, well, we do know it's degree 8, so it's 8c. And now we need to figure out, well, which term is it? Well, since we have an x here, so it's x, so remember the second number is just the exponent of our y, so it's going to be 3. This is basically our x, this is basically our y, so we could put that in. So we know x is to the power of n minus k, which is 5 in this case, 8 minus 3. And our y is negative b, and that'll be to the 3. Or, yeah. So now that we know this, let's just multiply out our combination. So 8c3 is 56. Sorry there. And we could just multiply this out. So 3 to the 5, 243x5, and we have negative b3. So at this point, we're really just solving for b, so we could just rearrange this. So then we could solve for b. So we're going to divide both sides by negative 56, 243x5. That way we could isolate the b by itself. So then these are gone. That is gone. When you divide these two out, you'll see that what you're left with is negative 125. So that gives us 125y to the 3 equals to negative b to the 3. Okay, and when you multiply negative b to the 3, it's basically going to be the same thing, but without brackets. I'm just going to rewrite it here. So it's basically the same thing without brackets. The two negative signs can basically cancel out. We could divide both sides by negative 1. So now we just need to cube root the thing. Cube root 125y3 equals to b. Oops, cube root it. 3. Gone, gone. And you'll be left with 5y equals to b. And that's it for the binomial theorem.